Good morning. Dimensional modeling. In this lecture, we discuss the principles of dimensional modeling, in what way the dimensional modeling is different from the traditional entity relationship modeling, different types of schema models, and finally we conclude this lecture by highlighting the various design steps associated with the dimensional modeling. Analytical requirements and subject orientation are the key differences between the data warehouses and operational structures. To build a data warehouse, we must map data to subject-oriented information by identifying business subjects, relationship between the subjects, and different attributes that are needed to represent each subject. Of course, modeling is an iterative process and tools exist today to assist the modeling. The relative data sizes in a data warehouse. Several years of data we can classify as older detailed data, current detailed data, lightly summarized data, and highly summarized data, and so on. We have sales detailed data during the period 1985 to 2005, which we consider as old data, and they are all scattered at various sources. Now we also have sales detailed data for the period 2006 to 2010, which we consider as a current data. Then weekly sales by product or weekly sales by subproduct for the current data. They are all available here. And finally, monthly sales by product for 2006 to 2010 are available here. And we can also find out weekly sales by region for 2006 to 2010 and monthly sales by region for 2006 to 2010. Typical data warehouse system. Data warehouse is developed by using different databases. In this diagram, there are three different levels. Top level is known as usage level. They are MIS reports, ad hoc reports, analysis, data mining. In fact, you can as well do deeper analysis using data mining by considering this data warehouse data. Bottom layer consists of different data sources, which we can as well denote as databases. Data in a data warehouse is either derived or selected from these data sources. Data sources are heterogeneous in nature. Middle level is called a data warehouse. The important issue is how do we organize the data in a data warehouse? Or in other words, how do we model the data in a data warehouse is the topic that we are going to discuss in this lecture. Let us quickly recap what we have discussed earlier. As per the architecture of the data warehouse, we have different sources which are of heterogeneous in nature, and the data from all these sources are extracted into the staging area where we clean and we transform, we validate the data, and also we may summarize, or we may aggregate, or we may populate the data marts, and ultimately the dimensional data and fact data are loaded into the data warehouse. So this is our data warehouse. So from this data warehouse, we are able to generate different kinds of reports, cubes, and we can do analysis, deeper analysis, etc. So data warehouse is a subject-oriented, integrated, time-variant, and non-volatile collection of data enabling management decision making. Actually, the dimensional modeling starts after collecting the requirements of data design for data warehouse. There are several phases prior to dimensional modeling. Dimensional modeling is an effective, efficient, and successful technique to design enterprise data warehouse and distributed data mart database schemas for maximizing the query performance. So the main modeling technique used in building the data warehouse is known as the dimensional modeling. So the dimensional modeling ultimately concentrates at this level. There are several phases. The slide shows different types of phases used prior to the dimensional modeling. There are requirements gathering phase, requirements definition document, information package, data design, and finally dimension model. From the requirements gathering phase, the data documented in detail in requirement definition document. A set information package diagram, which is one of the most essential document used for dimensional modeling. These basically used to show metrics, business dimensions, and hierarchies within the individual business dimensions. The information package diagrams form the basis for the logical data design for data warehouse. The data design process ultimately results in the form of a model called dimensional model. So for any kind of modeling, first of all, we have to understand how to design a logical model. A logical model is a representation of a business problem without regard to implementation, technology, and organizational structure. That means they are independent of these implementation, technology, and organizational structures. As you know, in databases, we use a popular model called entity relationship model to build a logical structure for a given application. The features of the logical model are: it represents business requirements completely, correctly, and consistently. It removes redundancy. It doesn't presuppose data granularity. Of course, it is not an implementation of the product, and it is an independent of DBMS. These are the features which are frequently used while building an entity relationship model for a given problem. The slide shows an example of ER model. Left side of the slide shows the ER diagram, and right side of the slide shows the dimensional model. If you see the ER diagram here, there are different kinds of entities, namely customer, invoice, product, and different kinds of relationships between the entities. So for example, order is a relationship between the customer and invoice. Similarly, order item is a relationship between the order and product. Invoice item is a relationship between the product and invoice. So whenever you model a ER structure, we always consider the efficiency of the execution of the application into account. But if you observe the diagram shown on the right side of the slide, which we call as the star schema. For example, sales is a fact table here. Customer, store, product, and period are the dimension tables which are linked to the central fact table to capture the measures, namely sales amount and sales quantity. So in the dimensional modeling, this type of diagram is known as star schema. Whenever you convert the logical model into a physical model, we always translate the specification of what is implemented. That means whatever the logical representation we identified, that is translated in the form of a specification for ready for implementation. The main features used while translating are optimization, efficiency, buildable, robust and flexible. For example, here how customer is represented, how product is represented, how delivery item is represented, how customer chargeable are represented. They are all represented by taking the different types of data types that are required along with the field description, field name, type, constraints, etc. So that means you are translating the logical model into a physical model in such a way that it is efficient, optimized and readily buildable, robust and flexible in nature. Now coming to the dimensional modeling, the process of building a dimensional model is termed as dimensional modeling. Dimensional modeling is a form of analytical design in which data is pre-classified as a fact or dimension. Such a representation improves the performance by matching the data structure to the queries. That is to say, from the analytical design or physical model in which data is pre-classified as a fact or dimension. Why are you doing this? The purpose of modeling this is to improve the performance by matching the data structure to the queries. For example, the type of queries the user generally poses is shown on the slide. Give the current period's total sales volume and revenue based on either product or by business unit and package or combination of all the three. So to optimize such kind of queries, we are identifying a suitable data structure in order to improve the performance of the query. Logical data modeling is the first step towards building a data warehouse. Dimensional modeling is a logical modeling design technique often used for data warehouses. It is a logical design technique to structure the business dimensions and metrics that are analyzed along these dimensions. We can also consider dimensional modeling as a technique for designing databases around measurable business processes. That means here the data is organized around business processes rather than the business entities. In databases, we design databases by considering business entities into account. But in data warehousing, we consider business processes into account to identify the business metrics. Dimensional modeling is a data modeling approach that stresses ease of use and performance. For any design process, requirement specification is important. What are the expectations from the data warehouse? How much user is interested to perform analysis is the key objective considered in dimensional modeling. Based on the requirements, how best we can model the data in data warehouse is driven by data modeling in such a way that query performance is optimized. That is to say, it is an approach of choice for most data warehouse teams when designing for end user access. Dimensional modeling is proved to provide high performance for queries and analysis. In view of these reasons, dimensional modeling is a basic building block in designing the data warehouse. The slide shows what is the foundation of OLTP systems for modeling. ER diagram is shown on the slide. Basically, ER diagram identifies the entity or entity classes, the attributes of each entity, key for each entity, and the different kinds of relationships and the cardinalities. The cardinalities can be either one-to-one or one-to-many or many-to-many. Different entities are connected through relationships. Another aspect is cardinality, how each entity is associated with another entity. Metadata is also used here while designing a OLTP system. We now discuss in what way dimensional modeling is different from entity relationship modeling. Entity relationship modeling focuses on discrete business entities, their attributes, and their relationships. Sound ER modeling technique leads to normalized data models, and normalized database design minimizes update anomalies. So that is to say, we always design database schema using the concept of ER modeling and normalization process. So normalization process helps in removing the anomalies and controlling the redundancy. In ER modeling, there is no explicit allowance for time. This is one of the drawbacks. And this is one of the major influencing requirements for building a data warehouse. As you know, ER modeling is commonly used in the design of relational databases, where a database schema consists of set of entities and relationship between the entities. Such a data model is appropriate for OLTP systems. However, a data warehouse requires a concise, subject-oriented schema that facilitates online data analysis. Design of models for data warehouses are different from entity relationship model. In data warehouse, most popular models are star schema, snowflake schema, or fact constellation schema. We now look at each of these schema types with examples. In ER modeling, as I mentioned earlier, there is no explicit allowance for time. So with the dimensional models, the main focus is on business processes and the entities that define the business process. Dimensional databases are usually denormalized and intended for read-only access. Dimensional models are time-oriented. The slide shows the basic differences between the ER model and the dimensional model. ER model is optimized for performing VML operations like insert, update, and delete, whereas dimensional model is optimized for querying by the users. In ER model, we can have more tables, less number of indexes, and more joins. But in the dimensional model, there will be less tables, more indexes, and less joins. That means you are optimizing the number of joins in order to improve the performance of the query. That's why joins are very less here, to speed up the query execution process. ER model is a conceptual model, whereas dimensional model can be considered as a logical model. ER model is a very complex for comprehension. That means it is very difficult to understand the problem and then construct the model, whereas dimensional model is very easy to understand. In the case of ER model, it is not easy to incorporate changes in the design, but that means flexibility is not very good in the case of ER model for changes in the design. But in the case of dimensional model, we can accommodate changes in the design. That means flexibility is very good in the dimensional model. ER model is normalized in nature, in the sense that whenever you convert the ER model into a relational model by using normalization process, we remove the redundancy and overcome the anomalies. Tables are broken into many small tables, so which is the decomposition process. In normalization, we widely use the decomposition process to overcome the redundancy and anomalies. But in the case of dimensional model, they are highly denormalized. Many small tables are combined together. That means you are grouping the tables into a single larger table, which introduces the redundancy. That is why it is a denormalized in nature. ER model is used for online transaction processing systems, whereas dimension model is used for online data analysis, which we popularly call as OLAP, online analytical processing. There are no standard methods exist to handle changes in the entities, but whereas in the dimensional model there are some prescribed methods exist to handle changes in dimensions. We now look at in detail about the dimensional modeling principles. So what is a dimension? As I mentioned earlier, dimension modeling is an approach to identify and design appropriate data structure based on the user and business needs. Dimension model consists of two different kinds of elements: facts and measures, and dimensions. What is a dimension? A dimension is a finite domain attribute defining minimum fact granularity. Attribute type generally alphanumeric in nature. Fact table is used to store the measures or business information. Dimension tables determine the contextual background to the facts. The term dimension represents a single category or perspective by which associated facts are interpreted and understood. For example, store is a perspective by which sales are understood. It is the answer to the question, where did the sales occur? A dimension table is a table which holds a list of attributes or qualities of the dimension most often used in queries and reports. For example, the store dimension can have attributes such as the street, block number, the city, the region, and the country where it is located in addition to its name. Every row in the dimension table represents a unique instance of that dimension and has a unique identifier called the dimension key. So therefore, a dimension table is a denormalized relational table that includes a surrogate key and a set of attributes belonging to a hierarchy. A surrogate key is an attribute whose unique values are automatically generated by a DBMS. Features of dimension tables. Dimension is identified by answering the question, how do business people describe the data that results from a business process? Entry into the fact table. In order to provide a value in the fact table, we must consider dimension as a starting point. That is why it is considered as an entry into the fact table. Or in other words, in order to design the fact table, first we should understand the dimension tables. Dimension is a denormalized in order to reduce the number of joins in resulting queries, which I have already explained earlier. Dimension attributes are generally static, descriptive fields describing aspects of the dimension. Dimension table is designed to hold infrequent changes to attribute values over time using slowly changing dimension concepts. We will discuss in detail what are the different kinds of dimensions shortly. Dimension tables are used in group by SQL queries. Dimensions simplify SQL group by queries. Every column in the dimension table is typically either the primary key or a dimensional attribute. Every non-key column in the dimension table is typically used in the group by clause of SQL query. So therefore, in order to build even a simple star schema, the first step is we have to identify the dimension tables first. Once the dimension tables are identified, all these dimension tables must be linked into a central table which we call as a fact table. If you take the combinations of these dimension tables, we will have several entries, several records or several rows in the fact table. A fact table consists of two different kinds of entries. First kind of entries are termed as key entries, and the other kind of entries are termed as measurable values. The key entries are nothing but surrogate key values, and for each dimension there will be a key associated in the fact table, and that key is linked to the dimension table. So in this slide there are 4 dimension tables, therefore 4 keys are used. Key 1 is used to link the dimension table with the key 1. Key 2 is used to link the dimension table with key 2. Key 3 is used to the 3rd dimension table. Key 4 is used to the 4th dimension table. Another example is, as I mentioned, dimensions are perspectives. For example, customer, geography, time. They are all different perspectives for the. Here store is a dimension, product is a dimension. Store key is a surrogate key for store. Store name, street address, city, state, region, country are the attributes of the store. Similarly, department, brand, product group, product name, product ID are the attributes for the product, and product key is the surrogate key for the product dimension. Star schema, as I mentioned earlier, all the dimensions are linked here to the central fact table called sales fact table, which is termed as store sales, and the name of the fact table is called sales fact table. And payment type, product, store, time, customer are the dimension tables. So single fact table is joined to a set of dimension tables, and it is simple, symmetric because structure is symmetric, extensible. I can add one more dimension and then without changing the structure I can compute the measures, and of course optimized. The number of joins are less. Whenever one dimension is added, one more join I am including here. Grain of the star schema is the grain of its central fact table. So grain means at what level the aggregation or summarization is computed at the fact table in the form of measures. So that is nothing but the grain. So this is our star schema. So it imitates the behavior of the star. Now the question is, how do we model the star schema? Whether to model dimension table first and fact table next, or fact table first and dimension table next. There are 2 ways to model star schema. We can start with dimension tables and then design the fact table. The other way is design a fact table first and then model dimension tables. We discuss with an example the star schema design based on the second approach. That means we are designing the fact table first and then dimension table next. In fact table, each record contains a primary key, which is concatenation of foreign keys to dimension tables. For example, here date, store, product and customer keys are combined. Payment type key, date key, store key, product key, customer key are considered as the primary key, concatenation of foreign keys to dimension tables. Then facts are measures identified by primary key. For example, price is uniquely identified by primary key. Quantity sold is uniquely identified by the primary key. Unit price is uniquely identified by the primary key. Unit sold also uniquely identified by the primary key. So in fact table design, we can model data at any possible level of detail. For instance, we could store information at a weekly level, not a daily level. That means sales per week can be stored in a fact table instead of storing daily sales. The level detail captured in fact table is termed as the level granularity or the grain of the table. That means at what level the data in a fact table is stored is known as the grain of the fact table. Storing data at most detailed level results in much higher disk requirements. It is always possible to recreate, aggregate summary data from detailed data, but we cannot recreate details from summaries. That's why choosing of grain is a very important aspect in the fact table design. The reason of having high disk requirements when you reduce the size of the grain is that we have to accommodate more data. If the level of the data is at the lowest level, then we need large disk requirements. If level of the data is at the highest level, then we need less disk requirements. So that's why, in order to provide the better analysis, depending on the business requirements, we need to identify the grain of the fact table. So each record in a fact table contains a primary key. Each fact or measure is uniquely identified by the primary key. The primary key of fact table is made up of concatenation of foreign keys to dimension tables. This is another example of a star. Already explained this earlier. Then coming to the dimension table design, a fact table is useless in the star schema design, in the sense that if you say, what does it mean that we sold 16 units of product key number 14 to customer key 174 on date key, say January 1st, 2010. It means nothing until we can decode these foreign key values. That is the reason why we need dimension tables to convey the meaning associated to each fact. So therefore, dimension table design provides meaning to each fact. It identifies the dimension elements, and the key feature used in the dimension table design is denormalization. Now let us see what is the difference between normalized and denormalized structures. The figure shown on the slide provides two different kinds of diagrams. The first diagram is called a normalized diagram, and the other one is known as denormalized diagram. In normalization, we are dividing a larger table into a set of smaller tables. A product is associated with many product lines, okay, and many units. And product line, many flavors may exist for each product flavor, in the sense that a larger table is divided into a set of smaller tables and linked. Whereas in the case of denormalization, all the relationships captured are grouped into a single table, which we call as the product table. That is, all the information regarding each dimension element appears on a single record in the dimension table. When loading dimension tables, we join many source tables together to put the result into one flat denormalized table. Each record in this table fully describes a dimension element. That is to say, we are pre-joining tables together, satisfying query time resource requirements with load time resources. Normalized and denormalized designs are shown in the slide. We now see what are the features of dimension table. Various features of the dimension table are: dimension tables are wide, they are short, the use of surrogate keys, it contains links to corresponding records in source tables, and it contains additional date and active flag fields. What is the meaning of wide? Compared to tables used in the traditional database applications, dimension tables are much wider. That means what? Width-wise, dimension tables are very wide. Here wide means that it has a lot of columns, lot of attributes. Wider columns provide more descriptive information. Wide dimension tables provide more attributes that can be viewed and summarized. That is the reason why dimension tables are very wide. Width-wise, of course, they are very wide, but degree-wise, they are very short. Degree means what? The number of rows in a table, or the cardinality of the table. Dimension tables are in general far shorter than the fact tables. For instance, each product may be sold thousands of times, and thus appear in thousands of fax records. Each appears in only once in dimension record. We can join very easily a short table with a huge table when the relationship between the two is a foreign key based. Hence, short dimension tables are very critical. Hence, the presence of joins, the star schema design uses relatively less number of resources as compared to many joins in other modeling approaches. Then the third feature is use of surrogate keys. A key with no independent of business meaning is termed as surrogate key. These are usually just a series of sequential numbers assigned to be the primary key for a table. These are useless for end users and are never queried by the end users. In the case of fact dimension table relationships, surrogate keys are used to provide very efficient relationship between these tables. Creating and working with surrogate keys is more beneficial than using the business keys. Then fourth feature is it contains links to corresponding records in source tables. That means the links are nothing but joins here. Of course, we can also add some more additional fields depending on the type of the dimension. The slide shows different hierarchies in each dimension. For example, in the store dimension, there is a hierarchy associated. There will be several stores in a district, several districts in a region. All regions becomes the total regions. Hierarchical relationship is one of the key feature available in the dimension table design, which is not there in the normal database tables. So the store dimension here has an attribute hierarchy of store to district, again district to region. Product is composed of products, products to brand, brand to manufacturer. Based on the simple model, we can see that the granularity of the data is products sold in stores by day.
Sir, I would like to ask, how is data warehouse schema design different from database schema design and what are its advantages?
Entity relationship modeling is used in designing database schema. You all know that ER model is basically used to represent the entities and the relationships among the entities. Whatever the schema you design using this ER modeling and normalization techniques, that schema is always useful and appropriate for online transaction processing systems. Coming to the data warehouse point of view, data warehouse needs concise subject oriented schema to facilitate online data analysis. Such a schema design is possible only when you take subject orientedness into account. That means you are integrating the data by considering all the data used by various applications in an enterprise by using the concept of subject orientedness. Coming to the second question, the key advantages of using data warehouse are easy data analysis, presentation of results in variety of formats. Then another advantage is offloading of queries from OLTP system, fast and flexible report production. From the application point of view, databases concentrates on application based integration, whereas data warehouse concentrates on subject oriented integration. This way you can compare data warehouse and its advantages with the databases.
So I want to ask that, can there be a cyclic refresh in fact consolidation schema? And can two-dimensional table refer to each other?
There is no cyclic reference in fact constellation schema. In fact, it is not allowed. For each star schema, it is possible to construct fact constellation schema. How it is possible? By splitting the original star schema into more star schemas, and each one describes facts on another level of dimension hierarchies. So therefore, the fact constellation architecture contains multiple fact tables that share many dimension tables. The main shortcoming of the fact constellation schema is a more complicated design, because many variants for particular kinds of aggregation must be considered and selected. Moreover, dimension tables are still large. That is why there is no question of arising cyclic reference in fact constellation schema. But however, multiple fact tables can share the same dimensions. To answer our next question, can two-dimensional tables refer to each other? So the answer is no. Two-dimensional tables can never refer to each other. Any reference is always done via the central fact table only.
I have a doubt. In fact constellation schema, can two-dimensional tables belonging to the same fact table refer to each other?
As per the design of fact constellation schema, two-dimensional tables can be linked into more than one fact table, but dimension table cannot be referred each other. Therefore, two-dimensional tables belonging to the same fact table cannot refer each other.
Sir, my question is this: what is the difference between key and measures?
The difference between the key and measure. Here key means a surrogate key. The system generated keys are called surrogate keys. Keys are basically used to link the dimension tables together to compute an aggregate value across these combinations of keys.
How does Snowflake schema minimize the redundancy?
How does Snowflake schema minimize the redundancy? As you all know, Snowflake schema is a variation of the star schema, and visually it looks like a snowflake. In this schema, some dimension tables are normalized. Normalized means what? It breaks the data into even more sub-dimension tables. The main aim of normalizing dimension tables is to reduce the redundancies. But of course, this may conserve more space or memory. On the other hand, efficiency in browsing may be lost in the Snowflake design due to the inclusion of more joins needed for the querying process. Therefore, this schema is not so popular as the star schema due to this reason. So performance wise, star schema is much faster than Snowflake schema.
Sir, is there any advantage of star and Snowflake over fact constellation model, sir?
Is there any advantage of star and Snowflake over fact constellation models? Yes, ease of use, ease of understanding, less number of joins are needed to compute aggregate measures compared to fact constellation schema. That means to say, star schema doesn't require more joins compared to Snowflake schema. Snowflake schema doesn't require more joins compared to fact constellation schema. Thank you.